According to the program, our next speaker was supposed to be Tamiyu Afiz Olimeli Khan. Unfortunately, we couldn't establish connection with him, so here with us we have Sheyi Topiogunji, who is going to take the floor for him. Sheyi Topiogunji is an international conference speaker and researcher in emerging technologies, with a background in electrical electronics engineering. He graduated with honors, earning multiple academic awards, and holds a certification in quantum computing from the US-based Coding School. Currently pursuing a PhD in quantum cryptography with AI at the Center for Research and Development of Digital Technology of the Instituto Politécnico Nacional. He earned a cum laude master's in digital systems through a federal scholarship. His research integrates AI and cybersecurity with publications in Springer and Scopus indexed journals. His professional journey includes roles in automation at Procter & Gamble, where he trained in Germany and Egypt, and people management at Hyatt Chemia. He also founded an AI education nonprofit and a logistics company, combining corporate and academic experience to drive innovation. I hand over the word to Shade.
Thank you for the introduction. Thank you, everyone. So I need to step in on behalf of my colleagues to save the day. He's having some connection problem. All the same, I'm going to present on solving Hamiltonian function of split transnorm qubit capacity compute with a resonator in cavity quantum electrodynamics. So this seems very bulky, but I'm just going to pick on some words here. So the first thing will be the transnorm, which is a short form of transmission oscillator. Transmission oscillator, but it stands on its own. Then we have the qubit capacitively coupled with a resonator. So here, kind of a quantum resonating circuit is set up, like the classical one where we have the RLC circuit, the resistor, the inductor, and the capacitor. So we have something that looks like that in this setup. So that's the main thing. Then here, there are some values that were obtained, some parameters that were obtained, eigenvectors, eigenvalues, and eigenenergies. Then some calculations that were done to really analyze the circuit. So the motivation behind the work is that there are different ways through which qubits could be generated and through which it could be engineered. We have the applications in quantum computing, in information science, and also in quantum engineering. But we know today that one of the main reasons why quantum computing has not gone to production scale or commercial scale is because of error and noisy environment. So it turns out also that this particular model, that's a superconducting qubit, turns out to be one of the models through which we could actually obtain a noise-tolerant architecture. And that is why any work that is done here is very viable, because at that time, at using this model, we have a situation where we have ultra-low temperature operation. Then, of course, the electrical resistance is at 0 level, so there is nothing that resists the current flow in the circuit. And, of course, there is high conductivity and low loss dissipation. And we know that when this happens, of course, the energy will, the thermal energy in the circuit will be reduced or brought low, and because of that, the thermal noise will be eradicated. So that's why it's a good idea that we process this. Then these are just the basic components that make up the circuit, the capacitor, the inductor, and then the addition here is the Josephson junction, which actually maintains the non-linearity for the circuit. Then we look at the quantum cavity, quantum electrodynamics. So we just want to see how the atoms behave in a cavity. So the relationship between atom matter in a kind of cavity enclosure. So that's the essence of CQED, to check what is the behavior of photons with quantum matter inside a cavity. And the major phenomena here are the emission modification, the absorption, enhancement, and the photon scattering, light matter interaction. But of course, in this quantum emitters part, we are working on the superconducting qubit. These are the ways through which we can actually generate qubit, but here we are working on this the superconducting qubit. And it's a kind of interaction where you have light and matter form that come together to interact in an hybrid form in a microscopic electrical circuit. How did we go about the design? Actually, I need to emphasize that this is actually a theoretical, physical-based work. So it's kind of physical work, physics that is actually theory-based, not like a real-world experimentation. But then the experiment is designed to have an Hamiltonian engineering where we have harmonic Hamiltonian, we have the anharmonic Hamiltonian. Why do we have the anharmonic Hamiltonian? The essence is to ensure that between the energy levels in between qubits, we don't have a situation where we have harmony. Because if there is harmony in between the two states, we will not be able to study each of the qubits individually, and it will be very difficult to see how the energy performs. So that's why the anharmonic part is very, very important. And of course, it is the interaction between the atomic field. Okay, so these are the ways the work is actually done. So there is the rotating wave approximation that was done in the generation of the parameters, then the perturbation theory. So these were applied in the work. And of course, the Jane-Cumming model that was designed around 1963 to study the interaction between atoms at different levels and to see how atomic states, how they behave. So this also was incorporated into the design. Then the theoretical solution that we obtained, of course, we have the tuning parameter, which is the difference between the Rabi frequency and the resonance frequency. The qubit frequency, then the coupling strength, because we are coupling resistor, inductor, and the Josephine junction. So there is need to have a strong coupling strength and to know what the value is, and the transition frequency also. These are studied. The entire work was done through Python. This is the configuration of the entire system. At the left-hand side, we have the Josephine qubit, junctions, which is denoted by RJI, LJI. Then the resonator that instantiates the equilibrium situation between the components. So this is where that is done. Then the right qubit, which also shows us the Josephine junctions, donated by RJ2 and LJ2. Then the entire freedom, there's something called degree of freedom of this setting, of this setup. It was instantiated by the V1, V2, V3, the voltage 1, voltage 2, voltage 3. So this allows us to have a kind of degree of freedom in the analysis we set up. Okay, these are the mathematical combinations of the total Hamiltonian operator, and of course, it's a quantized system. So this is the entire mathematical representation. The first line is the resonator energy, so which combines the charging and the inductive, that's the capacitor. We know that for a resonance to happen, the resistive part, the capacitive part, and in classical world, the RLC, the resistor, the inductor, and the capacitor must be at the same equilibrium. So, but in the capacitive situation that we're studying in this quantum system, we just have the charging part and the inductive part. So the R part is taken away and replaced with the Josephine junction. Then the second line is represented by the anharmonic oscillation times, which I talked about, that the anharmonicity allows us to properly study the variations or the behavior of the energy levels in between the two states. Without that, this study wouldn't be possible. Then, of course, the third line has to be the coupling interactions between the components that are used. Then this is the simplified version of it, because to really do a proper work, some part needs to be dropped, like we call it the dummy parts. The dummy indices are to be dropped, so we could actually concentrate on the real single qubit. And again, you remember in the setup, we talked about the rotating wave approximation. So this also was used, and it was used in essence of dropping the operational. So we drop the oscillating times. So when the oscillating part is dropped through this approximation, we'll be able to focus on the convenient parts of the equation. After the RWA was applied, that's the rotating wave application, the component is reduced mathematically to the set. And we have also the energy solution, which uses a perturbation theory to set up. Then it gives us the second order of correction, and it's represented by the equations shown. The atomic field interaction also, of course, we know when there is interaction between atoms in the cavity automatically an atomic field will be generated, electric field actually will be generated from the Josephine junction. And this also is a two-level system, and we have it inside a cavity, and this is also represented mathematically. So the simplified form turns out to be this, and the transition frequency is the combination of the omega, this is the omega, then the angular frequency of the Q1, angular frequency of the Q2, and added to the angular frequency of the Q3. This is referencing Jane Cummings, who actually who designed this kind of setup in 1963. Then the preserved by excitation numbers, we have this. This part is very important. This is the atomic field detuning parameter. So this is the Rabi frequency, and this is the resonance frequency. So the difference between these two gives us the detuning parameter. Then there is the matrix representation of the two, which is actually a 2x2 vector space. Then the eigenenergies that we obtained from the calculations is actually shown as this. So the fundamental constant, of course, we know that Planck's constant is a major thing in situations of this setup. The Planck's constant, the reduced one, and also the real one was used. Then the resonance frequency, this actually mimicking the classical electrical resonance frequency, where you have omega is equal to 1 over root square root of LC. Then the quantum numbers, of course, the number of qubits must be greater than or equals to 0. And of course, we have the quantum resistance, not the normal component resistance. The energy terms are defined by these notations, and of course the main monicity, which maintains the situation of studying properly the energy level in the system. The impedance, actually, we know that for equilibrium to take place, when equilibrium takes place in a setting, RLC circuit or RLJ circuit in this situation, the impedance or the resistance at that point will be minimum. And that point, we have the impedance. So the atomic impedance, or the anomic impedance we have here, is represented by this, which actually takes care of the EC, the energy of the capacitor, of the CR and of the CL, in addition to the quantum resistance. So when this is taken, we have the slack represented as this entirety of the anharmonic impedance. Then the operators that were used for the excitation and de-excitation, the Pauli-Zils operator was actually used, and to create and annihilate, that is to destroy the operators, we have to instantiate this dagger lifted. Then the frequencies and coupling, the main frequencies that were used, as I said earlier, the qubit frequency, the WQ, the resonator frequency, which set up the resonance in the circuit, and the coupling constant. So these are the frequencies and the coupling constant that we use. And at the end of the day, the qubit frequency, or the anharmonic Hamiltonian qubit frequency, is derived as this. The coupling strength also is derived as this. Then the terms are explained here. The detuning parameter, I talked about this already, the difference between the resonance frequency, the Rabi frequency and the resonance frequency, so it gives us the transition frequency. The measure of the sensitivity, that there is a Q factor, just like in classical electrical engineering, where you have the Q factor that takes how sensitive the entire setup is. So also we have the quality factor, but in the case of a qubit, and it's shown as this. The cavity decay rate, of course, because of the interaction of the atoms in the cavity, so there's going to be a kind of decay between the energy level to the other, is also represented as this. And finally, we have an anharmonic energy versus phase, where we plotted energy against phase, and this gives us a kind of wavy situation, which gives us a double well potential, which actually is a fine graph that shows the interaction between the energy and the phase angle as we study the component. Then the energy spectrum that was obtained were shown as this from the qubit. This represents the qubit numbers, the quantum number from n that's n greater than or equal to 0 up to the value we take it. So here 700 is plugged here. At the vertical axis, we have the energy level, and that means this gives us the spectrum, the rate between the gradient here between the energy and the quantum number is going to give us the spectral value of this entire setup. Then the summary so far in this work, again, I again say that is a theoretical based work. So that is, it's not an experimental based work. We had to do some theoretical simulation and theoretical calculations to arrive at this. But then we have this achieved. There is kind of engineered Hamiltonian operators that give us, that we achieve for split transmon, transmon qubit coupled with resonator. We obtained energy solutions for anharmonic and interacting Hamiltonians as shown before. Then we have a derived matrix, the 2x2 vector space that was generated for single qubit gate in cavity. Then we have this calculated key parameter, the transition frequency, which is a difference between the resonance frequency and the qubit frequency. Then, of course, the detuning parameter, the cavity decay rate, and the quality factor that gives us the sensitivity of the entire setup. Then the graph shows us the numerical and the visualization of the anharmonic energy and the eigenvalues as shown in the graph. Then future work would be to extend this to multi-qubit systems to see how it could be used for dispersive approximation of superconducting using multi-qubit systems, and also to study the effect of the coherence, because of course we know we use the rotating wave approximation, so we also need to take into consideration the flipping of the angle, the phases. So again, we could also study the effect of the coherence and the implementations of some quantum gates, and of course error correction. But I believe it to be a fine ride, because since we're using superconducting qubit, naturally the thermal energy is reduced, then error is actually reduced to the barest minimum. So it is expected that the amount of computation cost that will be spent on error correction protocols will be very reduced because of the advantage of the superconducting qubits we have already. Then of course the experimental validation with real superconducting circuits. So the application very wide, very wide. So we have a lot. Actually, the Nobel laureate for the physics this year, apart from the fact that they won it around the work on tunneling, they also incorporate into their work Josephine junction, if we realize that. So it's actually, it has a great way of application. So we can apply it to quantum algorithm implementations. And to round off, these are the references that we use for the work. Thank you.